Well, thank you very much for having me. It's a great pleasure to talk to you today. I'll be talking about some work I've been doing together with Donald Slater, mostly Donald going full steam, and I'm trying to hold on. This one's mostly for the glaciologists, but I promise I will, yes, Helen, I promise I will try and bring you all into the fold. Okay, so a quick outline. I'm going to just give a brief overview of different carving styles, and then I'll dive into a modeling question, and in particular I'll present an updated carving criterion for large tidewater glaciers. And then I'll look at how that criterion can shed light on observed carving styles. So we saw this beautiful illustration yesterday. This is carving at Antarctic ice shelves, and it illustrates how the spatial and temporal scales vary. You can have super fast disintegration, you can have that sort of regular carving at fixed sizes, and then you have these very infrequent, like on a decadal scale, through rifting carving of giant tabular icebergs. When we move to Greenland, the situation looks a little different. So I have picked this incredible time-lapse video, many of you know this probably, of a carving event at Ilulissat Glacier. And you can see, and this is sort of an unusual cascade of events, but you can see that the glacier repeatedly carves at full depth. And then typically it's sort of top-heavy and it flips one way or another. So I call this full depth carving or buoyant flexure carving. The other main carving type in Greenland, when you go to smaller glaciers, is what we typically call serac failure. And that's where not the full depth of the glacier front carves, but only parts of it, either above the water or underneath the water. And then you end up with like lots of little pieces floating around. There's my colleague Laura Stevens. You can see her here in the... I don't have a... Oh, wait. Here we go. All right. And so what Sophie Golliver and Ginny Catania have done recently is look at 10 glaciers in Greenland and classified them by type of carving. So what you're looking at here is the 10 glaciers and time series about 40 years and terminus change. So they've all retreated between 2 to 10 kilometers. And what you see is that they typically have a very specific carving style, right? So blue here is that full depth carving, which we see in these three. And then you have smaller glaciers that carve predominantly serac style. And I'm going to come back to this plot towards the end of my talk. So this brings me to my second part, which is how do we represent carving in models? And it's an open and long-standing and difficult question, right? So it remains challenging. There are a number of ways that people try and do this. There's also a number of ways to partition these. Common breakdown is that you say there's like rate laws, which essentially look at strain rates and velocities of ice sheets. And then there's position laws, which look at critical thicknesses or critical stresses. In particular, what I want to focus on is this crevasse depth carving law. And the reason why I want to do this, or to justify my choice here, there was a review here by Amaral et al. Where they say the crevasse depth carving model provides the best balance of high accuracy and low sensitivity to imperfect parameter calibration. I don't know whether everyone would agree with this, but it's a prominent way of representing carving in ice sheet models. All right. The problem with these to date is mostly that you need some ad hoc modifications, and I'll tell you exactly what that is in a second, and I'm going to suggest a way to resolve this issue. All right. So we're going to go back to some very basic glaciology here. This is the question of how deep would a surface crevasse penetrate. And so the way that people write this often is that you have the depth-dependent horizontal stress in the glacier. So that's the total horizontal normal stress is given by the difference between the depth integrated shear, the resistive stress, minus the ice overburden, which the ice overburden, the weight of the glacier, basically acts to close the crevasse again. And what Nye, I'm going way back here, right? So what Nye realized in 1955 is that maybe we can find out how deep a surface crevasse would penetrate by saying, okay, that's going to be at a depth where these stresses are balanced. That's the point to which the crevasse is going to penetrate. So we're going to have a critical ds. At that point, the total stress is 0, and then you can solve for the depth of the crevasse as a function of Rxx. You can do the same for the basal crevasse. It's a little more complicated now because you have water in the basal crevasse, and the water might not, so this is the density of the water in the crevasse here, and that's not necessarily seawater. It might be fresh or something in between, right? But otherwise it takes kind of the same form. Now, what's nice here is that Rxx is typically produced as a standard output for ice sheet models, and you can just put it in into this relation, and then you can calculate your crevasse, and you can predict whether there's going to be calving or not. So that's great, right? I don't have an ice sheet model because all I do is idealized. So, but we can make some progress by looking at the sort of making the approximation that we're right at the front here, because we can calculate Rxx analytically at the front. It's just the difference between the ice pressure and the water pressure. So it's given by this. So I'm going to look at the whole question in this framework. Now, in this framework, the surface crevasses, okay, I'm going to show a lot of plots like this. So we have the water depth here from 0 to 1, the relative water depth, yeah, the height is the thickness of the ice, and this is the relative depth of your water, of your surface crevasse, okay? So when your surface crevasse is 1, that would mean you're penetrating all the way through, okay? What you see is that if you're in totally dry conditions, right, you don't have water pressure at the front of your glacier, then your surface crevasse in this framework penetrates to 0.5. And then as you're entering water, that acts to close that surface crevasse, and then at some point you're floating and you have a small surface crevasse. For basal crevasses, it's a little more complicated again, but not too much. So here, you don't instigate basal crevasses until something like 0.7, and then they grow. As you enter more water, you have pressure coming in, and they open up the basal crevasse. And so if you add those two, that gives you the total fractional crevassing. And that's the black line here. Now what you can see, problem, it doesn't go to 1, right? The highest crevassing you get here is 0.5. So you don't get calving, and that is a long-standing issue with this approach. And so what people have done is modifications. So you can maybe add meltwater into the surface crevasse to enhance your pressure, and then that drives crevassing. Or you relax your condition. You say as soon as the surface crevasse reaches this dashed line, you allow for braking then. It always feels a little unsatisfying. And so what happened was that Roger Buck, a couple of years ago, realized that maybe the calculation was done a little wrong. So what happens is that as your crevasses penetrate, your horizontal stresses actually focus on the intact ice. And so you don't only have one relation for stress, but you have 3. You have 0 horizontal stresses in the surface crevasse, you have the hydrostatic equilibrium in the basal crevasse, and you have a stress concentration. So there's a feedback between crevassing and horizontal stress in the intact ice. And so what you then do is you say from stress conservation, you integrate this. Over depth, and you say the modified stress integrated over depth has to be the same as before, and then you can solve for the modified surface crevasse depth and basal crevasse depth. And it's surprising for a very simple idea. It's surprisingly complicated, but you can do it. It's just algebra. I note that you need a ice tensile strength in this case. So for 0 ice tensile strength, your crevasse would always penetrate all the way. So you need some strength. And if we solve this, and now I'm going to plot this, ta-da, this is the great reveal. You get beautiful crevasses, right? They are much deeper now, the surface crevasses. And then once you get a basal crevasse, it accelerates with that feedback. And at some point, you can't balance your horizontal stresses anymore, and the whole thing leads to calving. So that's great. Now we have calving. The two factors that I need for this to give us relatively realistic behavior is that I need the glacier to be stabilized by that ice tensile strength, sigma max. And so this is the plot where I don't have basal friction. And so in this case, right, my glacier would always calve when I get to 0.7 water depth. I would never have something that's floating or not. So I can stabilize that further by saying there's basal friction helping my glacier. And so here we have basal friction. This is the plot with basal friction. And then you get to this point where you instigate the basal crevasses, and then you make it all the way to flotation. Obviously, once you start floating, you lose the stabilizing effect from the basal crevasse, and you calve. So in this case, you calve at flotation. Now, there's a lot you can do here with the strength and the basal friction and the density of water in the crevasse, etc. The full discussion is in the paper, and I highly encourage you all to read it, obviously. But I just want to highlight one thing, because I think this criterion sheds some really interesting light on observed calving styles. So I'm going to do this plot, and Catherine, I'm sorry, we flipped the axes compared to your plots here. So this is calving front thickness on H and calving water depth on W. And so you can think of it like have a 400-meter thick glacier advancing into deeper and deeper water, and at some point it starts floating, right? And so whenever it hits that flotation line, it starts floating. And so you can put observed thicknesses and water depths on this. So we have all these observed glacier thicknesses here, and then the ice shelf thicknesses in yellow from bed machine. And now what we can do with our criterion is I can vary the thickness, and every thickness of my glacier gives me a different curve here. And there is going to be one thickness, one particular thickness, where we just about reach flotation before that critical calving threshold. And then once you make it to flotation, your stress doesn't increase anymore. So then you're stable. And that critical thickness is just a function of sigma max. And we picked 150 kilopascal here, and that's 400 meters. So that gives you a critical calving height of 400 meters. Below that, you can have a stable unconfined glacier shelf. And above that, your height is too thick, and you would result in calving. And what's quite nice is that this fits with existing unconfined open ocean ice shelves pretty well. Now, finally, when you're above H equals sigma, H sigma, above H sigma, you want to invoke some basal friction. And so that means as long as you have some basal friction, it will also allow for thicker, stable, grounded glaciers. And then once they hit flotation, you will lose that. So here, the gray is a calving regime. Everything that's white would be stable. And so the idea is ice, tensile strength, stabilizes below 400 meters, and basal friction stabilizes above 400 meters. And just to finish, looking back at Gulliver and Catania, what's really cool here, so here's my plot of the different ice thicknesses. If I look at the different types of calving modes that we have here, I can classify them according to my scheme. So between 50 and 250 meters, we would not expect full depth calving. We would only expect calving from vertical stresses. Okay, and I should have clarified this in the beginning, right? We do not account for vertical stresses and Serac failure. So these small glaciers, they're between 250 and 250 meters thick, they always just crumble, essentially, right? They don't have the giant calving events. Whereas you have the intermediate size between 300 and 400 meter glaciers that have mixed mode calving, and then you have the large ones that mostly carve through full depth. Yeah? These glaciers are all between 600 and 750 meters thick at the front. Now, Siladic is a very cool case because it retreated into deeper waters. So it was grounded in some shallow waters, and it had only 300 meters thickness up to 2010 or so. And so it was carving through Serac failure mostly. And then it retreated into thicker waters, so its frontal thickness actually increased, and it transitioned to large buoyant flexure carving. And so I think we can tell you why that happened, right? Because you transitioned from that mode where it's stable to something that's less stable. All right, so just to finish up, it's not a full carving law, but it gives you an idea of how carving happens at large glacier fronts. When you're below that critical thickness, you are stable regardless of whether you're grounded or floating. And if you're above it, above that critical thickness, you will start carving when you get to flotation. And that fits very well with our observed geometries of glaciers in Greenland. There's the paper. This time I made sure that this QR code works. And before I take questions, I just want to say, and this is kind of cool, we have a postdoc opportunity for ice-ocean coupling modeling at UW-Madison, 2 years of internal funding. So you wouldn't have to worry about federal vagaries. If anyone's interested, come talk to me. All right, thank you.
As I said, there's still plenty of time for questions, so if you have questions for Till.
Yes.
Yes. Shengon, go ahead.
Yeah.
Hi, Theo. This is great work. So I have a question regarding to the sigma max. You mentioned this tensile stress threshold. Is that different for different glaciers, and also does that vary in time, or is it just a constant value for every glacier?
Yeah. I don't know. It's a really good question, right? And so what is the tensile strength of ice near the front? I presume, there's, of course, there's, the crystalline strength of the ice when it's intact, but these ice fronts are not intact. The standard crevasse laws assume 0 tensile strength. Essentially, they just say, because you have the crevassing, like if you stress it at all, it'll break apart. But once you account for the stress concentration in the intact ice, it doesn't work anymore. You need some non-zero. 150 is something that's used fairly often in the literature, but it's not well constrained. It may vary depending on the situation. Yeah, I don't know, maybe some observations the modelers have more input on that. Yes.
Thanks. That was great talk. You have that beautiful plot where you show all the glaciers just above the line, and those are in the basal friction regime, right?
Mm-hmm. Yeah. Yeah.
So you should be able to calculate the basal friction that allows them to stay there. And I'm wondering when you do that, and I'm sure you have, do you get numbers that are consistent with independent?
Yeah. So we've done this is where I start. Like Lily was commenting yesterday, I start like flicking through. Where are we here? For this one, for example. Okay, so here's where we vary the degree of basal friction, right? And you can look at, so the basal friction the way it's represented here is essentially it's tau b, but times the length of between the crevasse and the front, right? You need to have a distance over which the basal friction is acting. And so you have to be careful and it's that product essentially. We put in fairly realistic values. We said that the typical length is equal to the height of the ice sheet. So there's that relationship. And then we varied between, I think, 20 to no, far, ooh. This is non-dimensionalized now, but it's like, yeah, around 50.
It looks like a factor of 10. Yes? No, just a factor of 4, I guess.
A factor of 4 here.
Yeah,
so
yeah.
when the basal friction is too high, then, okay, so what happens for the blue line here is that you actually can carve if you're still grounded. If your basal friction is not strong enough, then you can, then in this case you would carve while still being grounded. As soon as you drop with those dotted lines below that threshold, then that's what I showed. You would carve at flotation.
Great, thanks, really interesting.
Thanks, Eric. Alex, yes.
Hey, Till. Nice talk. So it seems like you've gone like halfway from nigh-zero stress to linear elastic fracture mechanics.
Mm-hmm.
Why shouldn't we go the last bit of the way and just do LEFM, right? Because you were talking about like intensification of stress over the intact ice column, right? In the LEFM framework, you would assume stress concentration at the crack tip.
Yeah.
Why shouldn't we do that instead, since that seems to be like from material science what we would expect?
Right, yeah. Well, the short answer is that this gives us a very simple relationship, right? That is just one step more complicated than, I'm not going to flip around now, but it's still an analytic solution of the crevasse depths, and so the idea is that you could just put it trivially into ice sheet models. So that's, I think that's the main motivation, yeah. I think it'd be a great next step to compare it directly to
Yeah, because like in
LEFM.
LEFM you would have a stress intensity factor, right?
Yeah.
Which are pre-calculated for simple
Yeah.
geometries, and I would imagine there might be a sort of analogous geometry where you could sort of compare what you're getting and how it behaves.
Yeah, and I think Ching Yao, they have looked at some comparison of that, and Neil Coffey, yeah.
Thanks.
Yeah, thank you.
Hey, Dale, great talk.
Yeah, hi.
Hey. So, yeah, I want to think about like the starting video you showed us where you have these like massive buoyant flexures and there's kind of this style of failure. You took us to the ice front, and then here we're talking about tensile failure. So I guess, can you help us think about whether the rotations that we're seeing after calving, is that driving the calving by torques, or is that a result of tensile failure?
Yeah, that's a great question. So essentially, and Donald and I have this master plan that we're going to combine. I think there's 3 factors really, right? There's vertical stresses, there's horizontal stresses, and then there's rotational stresses, right? And I've done quite a bit of work on rotational stresses, right? Where you have a non-vertical ice face, and so that induces tilting if it's undercut topward or underneath. And so I think ideally you would combine all 3 of them and you would have sort of a grand unified theory of carving in that framework. I think, yeah, you know, to a first approximation for large, especially unconfined ice shelves, for example, I would say maybe I don't know. I'm not going to say that because I spend so much time arguing that the rotational roles are so important. So I think yes, I think you need both. For this case of Ilulissat, I think it's the combination, right? You have a tensile strength. I mean, it looks to me, at first glance, it looks like it breaks off and it's not stable, and then it carves, and then it flips one way or another, depending on how it is. And also because if you've seen it, right, they flip both directions. One flips top forward, the other one the other way. So that suggests that it's not maybe a particular rotational event, but rather a stress event. Yeah.
Thanks, Till. I think we should keep going. Moving on to the next talk.